Right. Well, thanks everyone for coming. I'm going to give you a slightly different perspective from the panel on how to scale Ethereum. I think I have a very simple answer. We just need to rethink everything from a blank slate design, essentially. And I'm going to tell you about some of the design choices we've made at Hyle to do exactly that. So I'm Lancelot. I'm co-founder and CTO of Hyle, and today I'm going to tell you about our design choices, the reasons we made them, and how they can achieve enormous scaling on the L1 level. But first, let's talk about what's coming in the next few months, next few years. Obviously, I don't think anybody will disagree with me here. ZK is the end game. Zero knowledge proof technology is evolving rapidly. We've gone from having to write circuits, which are very arcane, to like being able to use ZK VMs and writing Rust contracts. And like people are making a lot of progress towards real-time proving, and I'm pretty sure we could expect to have like near instant proving on smartphone in a couple of years, or maybe a few more than that. And the tooling alongside of it is also vastly improving. So first trend that we're seeing is that ZK is becoming much more than usable. It's becoming actually commonplace. The second trend that we're seeing is that we're moving towards a signature by default world. And this has like a lot of reasons. One of the big ones is that you have to counter AI slop. And the only ways to really do that is signatures. And if you think about it, like ZK is kind of just signatures, but programmable. It's like the whole idea of programmable cryptography. And signatures are following the same kind of curve as ZK. You got emails being signed for a few years already, passports. Now we're signing invoices, contracts, open banking, as Noir did. We're going to sign photos, health data, voice stuff, IoT, pretty much everything. And so what happens in a world in which you have both ZK on the one end going real time and signatures becoming commonplace? Well, the thing is that something that's signed can be basically trustlessly brought on-chain with ZK. And so you can kind of bring like this whole new class of real-world assets on-chain that you can now trustlessly operate with, and that enables new kinds of applications. But you really can't do this on existing blockchains all too well, either the L1s or the L2s. I mean, I'm not going to say anything new here. Fragmentation, poor performance, unintuitive UX, you all know the troubles we have here. So the question is, well, how do you build a network that enables this golden age that's coming? And the basic idea is that we need an iPhone moment. There's like three main problems that we see and three big solutions to those problems. The first is that applications, smart contracts, are limited in code size and storage size. The solution to that is essentially to just not do any storage on chain. The second thing is that, well, if you want to use the chain, it kind of requires you, even with account abstraction, to have a mnemonic like the 24 words, and you have to install a browser extension, or you have to have a ledger device. The solution to that problem is something we call identity abstraction. And the third problem is that you have slow throughput, and the solution to that is to simply not do any kind of execution. So how do you actually do that? Well, first, to remove the storage is pretty straightforward. We've known how to do this in Ethereum for a couple of years. All you have to do is make everything a rollup. In rollups, the only thing that's actually being stored on chain over the long term is the state commitment, and 99.99% of the actual state of the applications is being stored elsewhere, hence the iceberg metaphor. And basically, this makes the L1 chain much leaner, but you still have, and like it also allows increasing the size of the applications because you're no longer limited by like how many storage variables you can use. So that's pretty straightforward. Second question is, how do you remove MetaMask from the equation, essentially? And the solution here leverages the first point. It's basically to think about what a wallet is at like a philosophical level. It's basically just a secret, which is something that you are, something you have, something you know, and a nonce, a number used once. The role of the secret is to protect your identity, and with ZK, you can use a lot of other things to do that than private ECDSA keys. You could use email one-time passwords or just regular passwords. You could use passkeys and WebAuthn. You could do biometric stuff like WorldCoin's been doing. The other side of this is the nonce, used to prevent replay attacks, essentially. And nonce are very annoying because they're like planetary scale global state, you have immediate parallelization problems. Solutions here involved leveraging more state, and you can only do that if you don't have the state on chain, such as multidimensional nonces, or like using UIDs for each transactions and Bloom filters to check they've already been used. And you can do that if you do the first thing. The final item on the roadmap, which is the difficult one, is to remove the execution. And the solution here is, again, something that's part of the Ethereum roadmap, insofar as there's one for a few years. Basically, all you have to do is do sequencing. So the key insight is that sequencing is enough to achieve deterministic state, unless we're talking about intents, separate topic. Basically, if you start from a known state, and you process some transactions in a certain order, doesn't really matter how you do the execution, you're going to end up at the same result. Everybody's going to agree that, well, we started from $5 for John and we've ended up with whatever I wrote over there. So sequencing is enough for deterministic state, and deterministic state is kind of what you want in a blockchain. But how do you actually do that while iterating the base layer security? So my graph is pretty, well, I'm a little bit of a clown as well. Basically, if there's a clown, it means that it's not being done on the L1, so you don't inherit the base layer security. Otherwise, it means you do. And so basically, we were looking at ZK rollups. The sequencing is usually done on an L2 directly. Like it's usually a centralized L2 sequencer run proprietary. The execution, however, is kind of secured by the L1. So it's a clown with glasses. Because you do optimistic proofs, fraud proofs, or you do ZK proofs. And it ends up being impossible to kind of like cheat. But you get increased latency. You get potentially censorship issues. And then you got the DA problem. Some chains, some rollups send the DA of the chain to Ethereum. Some don't. And that's kind of awkward. The next iteration into like inheriting the base layer security here has been base rollups, where sequencing ultimately is done by the L1. Execution is done off-chain, but you couldn't easily prove it with ZK proofs or optimistic fraud proofs. And the DA is also being provided by the layer 1. And at Hyle, I'm going to introduce to you like a secret third thing, which is kind of the next evolution after that, which does all of those things directly on the base layer in a trustless manner. Our take is basically that ZK proofs are the best execution layer. This kind of like quirky graph is basically showing that with ZK proofs, you can do state transitions. You just change the state commitment every time. It works great. You have like infinite scalability. And you have much more flexibility in the kind of applications you can write. I'm not going to be talking about privacy, but that's one of the things, that's possible, obviously. If you're not doing validity proofs, but proper ZK proofs. So where's the catch? Because this all sounds way too good to be true. And if you think about it, well, there is a catch. There's 3 of them, actually. The first is the composition problem. It's quite difficult to call other contracts with ZK. Existing solutions, you have to go for bridges, you have to do shared sequencing, which is still like pretty awkward, and people don't really know what that is. There's the proving problem, obviously. It takes time to generate the proofs. It adds sequencing latency if you have to wait for the proof to be sequenced. And then there's the big one, which is the parallelization issue, which is kind of like that ZK isn't commutative in some way. And so let me get into more depth for each of these problems, how we solve them at Hyle. And that's what we're doing with pipeline proving. So first, when you're using ZK, usually, if you want to do composition, you actually have to do recursion. In a way, it's kind of like doing OP versus composition. If you want, say, have a ZK Tetris game and you want people to prove that they own a CryptoPunk because for some reason NFTs are back in fade, you're going to have to verify the proof that you own a CryptoPunk inside your ZK Tetris game. And so if somebody ever wants to change the CryptoPunk verification logic, or if you want to change the Tetris logic, you kind of have to change both at the same time. Which makes it awkward. It's not very flexible. You can't support too many things automatically. With proper composability, which is given to you if you have like shared sequencing at the layer 1 level, you can have just the CryptoPunk contract doing its own thing, and your ZK Tetris contract just expects that there is a proof of a CryptoPunk ownership without necessarily having to recursively verify it. This also allows you to use different proof systems for each of these things, which are quite an interesting design element. because there's like different trade-offs to these ZK VMs and ZK DSLs and things like that you can then leverage. Because writing a verifier for Noir in Circom just isn't very fun. The second problem is the latency issue. So if, let's say, like for a very simple example, you got an auction, you want to make a bid on the auction finishes in 10 seconds. You could send a transaction, but by the time your proof generation's done, well, the auction's ended. And so you're unhappy because you haven't been able to send your transaction. Pretty straightforward issue. Nobody likes that. The harder problem is parallelization. And if you look at like the documentation for like the Mina protocol or Maidan, or a lot of people, like everybody struggles with this. Basically, if you do ZK proofs for state transitions, you have to start from an initial state commitment. And so if two people see the same initial state and they send each their own proof, well, whoever gets there first is going to deny the ability to process the other proof, because we've gone from a green state to a blue state, and the other guy, he expected the green state to the red state, and we just cannot transition from the blue state to the red state. We don't know what's happening there. And so again, annoying because your transaction doesn't go through. So how do you fix both of these? Well, our solution is pipeline proving, which is quite similar to, for example, what Monad has been doing with deferred execution, but taken to like the ZK realm. You first do sequencing. You send blob transactions secured by the L1 that tell what you want to do, what you essentially commit to doing. If it's an auction, you say, well, I'm going to bid 10 USDC on this NFT. And then once the transactions have been sequenced, to settle them, you send the proofs in a separate, separately. That allows you to send the proofs on a based known state, because if you're trying to prove the second transaction in this example, well, you're going to see that the first transactions arrived before you, and so you're going to base yourself on that state and not on the initial state you were seeing initially. It also fixes the latency issue, because sequencing is enough for deterministic states. So long as you're confident that your proof will arrive, you know that your transaction will be settled. And you can take days to generate your proof if you feel like it. I mean, in practice, we're not going to wait for days to do it, but conceptually, latency of ZK proof generation is just no longer a problem. And that's kind of like what we've been doing at Hyle, and it enables what we call unchained applications, because they're no longer limited by the chains. They're no longer restricted to what blockchains can do. You can do much more things on top of like those ZK rails at the base layer. I'm giving random examples here. You could do like permissionless peer-to-peer on-ramp with ZK email. Again, like this can be done today with Noir and implemented in real time at Hyle. You could have like a fully on-chain game where the state is decentralized by the players of the game. You could do DeFi pooling with permissionless private strategies, because it's ZK, so you can have privacy on a centralized backend, and you can still have like trustless composability, trustless escape hatches, things like that. You could do things that are like variants of WorldCoin. You could airdrop a whole country, because you don't have the state on chain. You don't need to know who the people are. You just need to know how to verify proofs that they have a passport from a given country or something like that. Really opens up a whole world of possibilities that just aren't really possible on existing chains. And even if you're trying to like use more specific rollups, if your solution to your problem is to add more blockchains, I think you're not really fixing it, whereas I believe our solution does. So that was Hyle. We're going to be releasing our testnet in a couple months. We're going to be also building some applications on SDK, and we've got a lot of like institutional knowledge on how to write these things at this point. So if you're interested in doing this kind of thing, feel free to reach out. This is our Telegram. We also respond on Twitter. I'm going to be hanging around for a bit. And we do grant programs or co-grant programs if you're interested in building with us. Thanks for coming, and I hope you have a good day at ZK Hub.